Welcome to part 2 of this video tutorial for the fatigue analysis of a cylindrical rod subject to reverse bending. So just to remind you, in part 1 we created the static study for this particular cylinder, right? So we created this cylinder that is 25 diameter, has 250 length, and we analyzed it to this stress of 1500 Newton. In the static study, of course, we applied this as a static load over here and we calculated the von Mises as well as stresses as well as the displacement. Now, in this part 2 of the video, I will show you how to progress the problem to the fatigue analysis part. So what we need to do is we need to now go and create a new study. And in the new study, we will choose fatigue as the type. And in the fatigue type, we will choose the constant amplitude events with defined cycles. There can be other types of events as well, like variable amplitude history and harmonics and random vibrational analysis as well. But that is beyond the scope of what we are covering in this tutorial. So we'll go for constant amplitude of the with defined cycles. You can give it the name of your choice. I'll just call it as bending fatigue. So that's my study name. I'll click on the green arrow to basically set up the study. Now, once we have created the study, the next step is to add a fatigue event. So to add the event, we keep to the default values of 1000 cycles, and in the type of the analysis, I'll choose fully reversed. So keep this in mind. This is same as what we have already, covered in the class about the different types of events. So you can have a fully reversed scenario, you can have a zero-based stress, you can have analyze a case with a particular loading ratio R, or you can even have a fatigue event that has separate loads with each one having its own maximum. So you can have separate alternating loads with basically the analysis can then consider the combination of peak from these different loads and then determine the component that produces the largest stress. But right now, our case is the case one, which is fully reversed loading. So going back to this, so in this, we just simply select these default options. This is important that this should be set up to the same name as your static study over here. So if for whatever reason you don't find it there by default, then you must change this to the particular name of the study. So we click on this green arrow and now our initial analysis setup has been completed. But next step is to basically input the value of the SN curve. So basically, whenever we are analyzing parts for fatigue, we have to input the fatigue data. Now, for real components, the fatigue data can be obtained experimentally, or you can obtain it from softwares like Current IQPAC, or you can just simply define the values using approximate equations from the literature. So in this case, that is what we are going to do. And to help you populate that data, I have already provided you with this SN calculator, which is basically modified from the solution provided by SolidWorks for this particular solution for the curve calculation for steels. So this Excel file, which is already uploaded on your D2L, is called as SN calculator. So in this file, what you need to do is you have certain variables that you need to look into. So if you compare this Excel file with the data over here, you can see that you have these certain points. So let me actually open both of these side by side, so it's easy for me to discuss them. And right, so that's this file, and that's this file. Right, so you can see here that you have got this n min. So basically, this is the number of cycles that define the transition from low to high cycle fatigue. In this calculator, this has been set to 1000. You can change this if required. The maximum number of cycles is being defined as 10 to power 6, and then the curve actually goes to 10 to power 7 later on to represent the endurance limits of the steel. So the curve always starts from ultimate strength. Right now you have got a 1 over here, but this number needs to be replaced by the ultimate strength of the material that you are considering. So, for example, in our case, we have the material is basically AISI 1020 steel, right? So we will basically go to that, and if you go into apply edit fatigue data, you can go into the fatigue SN curve. This is where you will finally input the values from your calculator. But right now, I just want to go into the properties of this material, and you can see here that the properties are given as tensile strength is 420.507 megapascals, right? So I will basically take that. So this is my ultimate strength value. So 420.507. So I will basically go and enter this number 420.507. Now keep this in mind, this unit must match the unit of the values that you input in the SolidWorks. So because I set up my analysis in megapascal, that therefore I'm right now keeping these numbers in megapascal. Otherwise, if you set up your analysis in Pascal, you'll have to change accordingly. Now, the by default, the value of the endurance limit is basically kept as half 0.5 of the C24. This is a typical estimate for steels under bending fatigue. So basically, we are taking it as half of the SUT. If you have experimental data that suggests otherwise, you can of course change this number as well. Then with this F is basically the combined factor for different things like the loading as well as the, for example, the machining condition, the polishing condition. So all of those factors will be discussed in the lab for different cases. But right now, we are sticking with the number provided to us in the example. And that number is, let me just quickly check that, it is 0.7854. So the endurance limit modification factor is over here. So this is the value of the K. The value of F in this case is being kept same as 0.9. Okay, so let me recheck that. So in this particular case, the value of F, because this F is the fraction of SUT for the basically at the transition from low to high cycle. Okay, and this again is the same. We've used the same estimate in your other tutorial problems as well. So this F factor is kept as 0.9, whereas this K is the endurance limit modification factor, which represents the effect of the various conditions, such as the machining, such as the heat treatment, and others. So for that, we have been given a combined value of 0.7854. So 0.7854 is the endurance limit modification factor, and you can immediately see how that then changes all of these numbers. Okay, so now we have got on this uh, uh, in this table, we have got basically all the numbers that we want to input. Okay, now he has set up his model as Newton per meter, but meter squared. But in my case, I've set up my model in megapascal. I'll go back and verify this from the fatigue SN curve option. So go back to fatigue SN curve option, and in the units, I will now set it up to megapascal. So once I've set it up to megapascal, I can now basically simply copy and paste my data. Okay, so copy, and paste, right? Control C and Control V. Now, because the stress ratio is -1, this is already defined here. We have a log-log plot. If you had a different ratio, your different curve, you can also input that here over here. But right now, we just have one particular curve. So I'll click on Apply, and this data will therefore now be applied to my material. Okay, so with this, our initial part of the setup is complete. I'll close this. The properties have been assigned to the material as user defined over here. Next, what I need to do is I need to set the fatigue study parameters. And to do that, I will basically click on the properties. Okay, so okay, so I will go and click on the properties. So in the properties, you have different options like random interactions, stress intensity, and the mean stress. So basically, we are not using the fracture toughness based criteria, so we can't use the stress intensity. Rather, we are using a stress life approach. So we will basically use the equivalent stress, which is von Mises that we have calculated in the static part. So this needs to be consistent with the static analysis that you have done. So if you use a different method, then you can use basically one of those methods. Now, then we in the first one, we after this, basically we don't need to change the mean stress correction in this case because the mean stress is 0. If there is a mean stress, like it will be the case in your assignment problem, then you'll have to choose the required estimate. For the fatigue strength reduction factor, we are already corrected our data for that, so we don't need to change that factor at this stage. And with this, then we will basically be able to uh, uh, accept these values. Uh, so keep this in mind that maximum absolute principal stress criteria is typically used for brittle materials. So if your material happens to be brittle, like gray cast iron, then you can use this instead of von Mises. But then you must have that as an output in your static analysis as well. Okay, so keep that in mind. Now, with this, we just simply click on OK, and I think this will then allow us to save all of these settings. Now, when this is done, all we have to do is run this study. So once you run this study, by default, you get two different plots. One shows the damage, okay, and the other one shows the life. Okay, so you've got both of these plots that are available to you. If for any reason you don't have the particular plot, you can you can basically edit the definition by clicking here, and then you can select on the plot type as either life, damage, load factor, or biaxiality indicator. So right now we are interested in knowing the life. So basically, this is the type of plot that we want to create. Yeah, just a bit of more explanation. So basically, life here means the number of cycles to failure at each location on the part. The number of cycles in this case is based on the SN curve and the alternating stresses at each location. A yellow basically indicates suggested bold fonts. A damage, uh, sorry. The damage option would basically show the percent of life of the applied loads have expended. Load factor basically shows the load factor safety at each location. So basically it is the factor of safety. And the biaxiality indicator plots the ratio of the smaller alternating principal stresses to the larger alternating principal stresses. A value of -1 indicates pure shear, and a value of 1 indicates a pure biaxial state. So right now we'll just focus on the life plot. So we can now basically check the life if we want at our selected location. Now you can see here that the life is less than infinite life. So for majority of the cylinder, which is the blue, you have got an infinite life. But then for a particular zone, you have got a finite life indicated by this red color. So let's actually look into some of those numbers. So we can actually click on selected entities. And in this case, if I select this edge and update the plot, I will be able to see the life. So you can see here that when it enters this red zone, this is where the life is much, much smaller. So this is the critical portion of my cylinder, where the life of only 223,214 cycles. So it's slightly above 223,000 cycles before the cylinder can fail. So basically, that's going to be the maximum life of this cylinder. You can basically use the probe tool to also probe on other points of interest from the graph to more uh, quickly look into the numbers. You can see here it is 8.102 into 10 to the power 4 cycles, whereas on this one, this is 5.249 into 10 to the power 5 cycles. So as you're moving away from the from the fixed edge, the life prediction is increasing, but obviously for a particular case, the most critical location will be the one with the smallest life estimate. Okay, so this is something that is there. You can go into the edit definition and chart options, and you can actually ask it to give you the maximum as well as the minimum values of the plot. In this case, the critical number is not the maximum because that's just the maximum life. It's actually the minimum life that is there. And in this case, the minimum life is 5.332 into 10 to the power 4 cycles. Or if you write it like this, then you can see that it is around 53,318 cycles to failure. That's the minimum life. Okay. We will use the value on the split line to compare with our analytical solution, and that's something that I will do in the third part of this video. Thank you. So that's it from the point of view of SolidWorks analysis. But in the next part of the video, I will compare these numbers with the hand calculated values.